Hello everyone. So welcome back to the lectures on the physics class 12th chapter 3 current electricity. This is the second lecture. So before this in the last lecture we had learnt about how steady current actually flows between two terminals or two ends of a conductor, and we also derived the relation between the current that is flowing and the amount of charge and the time. And we also saw a very important physical law that comes into play when we are considering the current passing through a certain material. It can be a conductor, it can be an insulator, it could be a semiconductor. So we talked about the Ohm's law, which gave us a relation between the potential difference between the two ends of a conductor and the current that is passing through it, and how much potential difference is going to be developed or potential drop is going to be developed between the two ends of the conductor is actually it's a function of the current that is passing and also the type of material that is being used. Okay, so the physical property of the material that influences the voltage drop across the conductor is the resistance that is provided by the material, and in turn resistance is a factor that depends on the resistivity of the material. Okay, so resistivity differs from material to material, and hence the resistance offered by that material to the passage of current through a conductor is actually then in the end influencing the voltage that is the potential drop that we are going to see between the two ends of the conductor. Okay, so we learnt about that. We saw how the Ohm's law is how the Ohm's law is stated, how it is given. Then with resistivity we also found out another quantity, that is the conductivity. So conductivity is the reciprocal or the inverse of resistivity. So a very simple way to understand, if a material is has higher resistivity, its conductivity is going to be lower, and if it has a low resistivity, then the conductivity of the material is going to be higher. Okay, so we had learned about all of this in the last class. So today we will try to see about the different resistivity of the different materials. Okay, so based on the this property, the resistivity, we can divide materials into three kinds of categories. So you have the conductors, you have semiconductors and insulators. So usually conductors, okay, they have very low resistivity. Okay, so low resistive material are going to be good conductors of electricity. Okay, you can see that most of the conductors have the resistivities in the order of 10 raised to minus 8. Okay, so that is pretty low, and in the same way you can see that the resistance values of uh, insulators, you can see that the resistivity are in they are of higher orders. You can see 10 raised to 5 here, then 10 raised to 10 to 10 raised to 14, also up to 10 raised to 16. Okay, so you can see that these insulators have high resistivity. That means that they are poor conductors. Okay, they have poor conductivity and hence they are poor conductors of electricity. Now semiconductors, obviously these are they can be enhanced to be conductive. Okay, hence they are called like semiconductors. So as I have already mentioned that you have metals which have low resistivity. Okay, that is in the range of 10 raised to minus 8 to 10 raised to minus 6. Okay, this is supposed to be ohm meter. Okay, this is not W, this is ohm meter. This is ohm. Okay, This is not W, this is ohm meter. Okay, so if you draw on a spectrum, so you will have the conductors here, or at one end you will have the insulators on the other end, and semiconductors are going to fall in between of the if you say the resistivity is increasing from left to right. Okay, so this is a simple understanding of how how we can classify the materials that we use for our different appliances and circuits on the basis of the resistivity values. Okay, so which are the inherent property of the materials. Okay, if you remember, we had talked about that how materials are, how can we call them as conductors, because they have, those free valence electrons which can, move within the material itself, and because of the movement of these charges, there is going to be, potential difference that is, being caused, and that is why the current can flow from one point to the other. Okay, so that is why we have the conductors, and in insulators, as we can see that the charge is not very free to move. Okay, so they accumulate at only one place, wherever your charge is getting induced. So then it does not and it does not allow the passage of the current, because the flow of the charges is not the same. Okay, then obviously when we are making circuits, how do we use these conductors or these insulators, okay, to kind of either allow more electricity, allow more current to pass through it, or limit the current that is passing through it. So what we use is called a resistor. Okay, so we use uh, an item that is called a resistor. So this resistor is usually made mostly from carbon. Okay, so these carbon resistors are very compact. They are not very costly, and that is why we have a wide variety of usage of these carbon resistors in the electronic circuits for different appliances. Okay, and because the carbon resistors are so small, we need to know the value of the resistance that it is going to give us. So to understand that, they have, when these were created, a color code was created along with it. Usually you will see some rings painted on the resistor like this. Okay, so usually you have, two kinds of resistors. We can have wire bound resistors or carbon resistors. So usually we use the carbon resistors as I just said. Okay, and usually these resistors are not very they don't vary a lot. The resistances of these resistors don't vary a lot according to the temperature. Okay, so that is why they are a good material to be used as resistors, the carbon resistors. Okay, so you can see over here that this is the resistor. This is like a small cylindrical kind of a body, and you put colored rings. Now each ring, the color as well as the position has a significance. Okay, so the first two bands, if you see over here, okay, so these are the significant figures of the resistance in ohms. Okay, so these are usually integers. Okay, so the first two bands that you have, band number 1 and band number 2. Okay, so these are going to give you the kind of the figures, the resistance in figures. Okay, so either in like tens, or you will have it in mostly it's like the 10s unit and the unit. Okay, So, and then the third ring that you have, okay, so the third ring is going to give you the multiplier, okay, the order of the resistance. Okay, so usually if we are considering these to be like, insulators, so these are going to have, higher order. Okay, and the last one, okay, the fourth ring is going to give you the tolerance. Okay, or kind of, how much the value of the resistance can vary, okay, from the indicated values. Okay, so obviously it's not always possible to give you the exact values of these resistors. So these color coded rings actually help us in estimating the value of the resistance that is being used in a circuit. Okay, and if the last band, okay, if the last band is not present, then by default we take the tolerance of say 20%. Okay, now if we try to find out the the resistance based on the color code that is given over here. So you have first as red. So by here you can say the number that is associated with the red is 2. Okay, then the second one is also red, so you will have 2 2. Okay, so you will have 2 and 2. This is a whole number figure, okay, which is associated with the resistance. Then you see again it is red. Okay, so the corresponding multiplier with the red color we will give as 10 raised to 2. Okay, and your last band is silver. Okay, so usually you see over here that if your last band is silver, okay, so this, the number column is going to give you the significance in the first two bands, okay, band number 1 and band number 2. This is for the third band, okay, and this is for the last band. Okay, so now the fourth band is silver, so we are going to consider the value corresponding to the silver in the last column. Okay, so you can see that is 10. Okay, so this so this is in ohms. Okay, and so this entire thing, this is what we are getting with the color code. Okay, so this is an approximate. So how much tolerance are we giving this resistor is plus minus 10. Okay, because silver band, the last band corresponds to the the percentage tolerance of value 10. Okay, so this is how we can find out the resistance value of the resistors that are being used. Similarly, for the second one, if you see that we have the first band, second, third and fourth, all are of different colors. So if your first band is of yellow, you go to this table, so yellow is 4. Okay, so since this is the first band, okay, so we are going first band, yellow band. Okay, then even the second band is the purple, okay, or violet. Okay, so you can see that since the first column is going to give you the values of the first and the second band, we are going to search for violet here, so that is 7. So that becomes 47. Okay, into the multiplier is going to be given by the brown ring. Okay, so again over here you search for brown, and now you go to the second column, so that is 10 raised to 1. Okay, this is the multiplier, so that is going to be 10. Okay, and this is going to be ohms. Okay, and then you put the tolerance. Okay, so that is going to be plus minus gold band. Okay, so the last band is the gold band, so we are going to check the value that is there in the last column, so that is 5. Okay, so the tolerance is only 5%. Okay, so this is how we calculate or we find out the resistance values of different resistors that are being used in the electrical circuit. Okay, so this is important to know because when you design the circuits, you need to know how much of the resistance do you want to kind of provide to the circuit that is being used or that is being designed for a particular appliance. Okay, so that is the significance of these resistors. Now we will see that obviously, since we said that resistivity is a physical property of the materials being used. Now there are some factors which can vary. We have already seen how the resistance and the resistivity can vary with respect to the length and the cross sectional area of the resistors. Okay, so now another factor that we are going to see is the temperature dependence. Okay, so usually the resistivity of a material is actually dependent on the temperature. Okay, so but the dependency does not have a very similar relation with respect to the all the different kind of materials that are there. Okay, so there is a range of temperatures, okay, where the resistivity of a metallic conductor is going to get influenced by the temperature. Okay, so over here we consider rho T, that is the resistivity at a temperature T, at any temperature T that we want to find out what is the say the resistivity of material at the certain temperature. Then rho 0 is the the reference resistivity that you find at the reference temperature of T0. Okay, so this is the relation that we get. Rho T is equals to rho 0 of multiplied by 1 plus alpha T minus T0. Alpha is the temperature coefficient of the resistivity. Okay, and it is termed, or the dimension of it is the inverse of the temperature. So if your temperature is in, say, Kelvin, so this is the the coefficient, the temperature coefficient is going to be, the unit of it is going to be Kelvin inverse. Okay, so that is the significance of this. Now if we plot the graph of, say, rho T, okay, at at different temperatures against T. Okay, so it should be a straight line, because you can see it's like straight line kind of a relation. But there are sometimes some materials where the straight line is kind of not uh, it's not the way it is followed. Sometimes you can see that for copper, you can see it is not a straight line. For nichrome it is a straight line, but it is not from the like the origin part. Okay, and you can see for a semiconductor this is a very steeply decreasing with respect to the temperature increase. Okay, so you can say that a semiconductor, okay, it will lose its resistivity, or it will become less and less resistive with increasing temperature. So you can see that semiconductors are highly dependent on the temperature of the, say, the condition where we are using the resistors, or the material for the resistors. Okay, so over here also you can see that at temperatures much lower than 0 degrees, okay, 0 degrees Celsius, the graph is going to deviate from the straight line. Okay, so that is another exception, that if your temperature is much lower, it is going to the straight line characteristic, or the straight line relationship between the temperature and the resistivity is going to be lost. Okay, so this is the influence of it. Now we can there is a way that we can describe this dependency in terms of the resistance, and also a qualitative understanding of it. Okay, so if you remember, in the last class we had derived that resistivity is the inverse of the conductivity and vice versa. Okay, and conductivity is given by sigma is equals to n. Okay, that is the your number of free electrons near E square. Okay, your charge and the relaxation time tau, okay, divided by your mass of the electron. Okay, so this is your sigma, your conductivity. Okay, so inverse of this is the resistivity. Okay, so we can see that the resistivity inversely depends on the number of the electrons, okay, per unit volume, as well as the average relaxation time between the collisions between the electrons. Okay, when your current is passing, the electrons are moving. Okay, so if we increase the temperature, the average speed of the electrons, which actually act as the carriers of the current, because they are the the charge carriers, it increases. Okay, and you can see that the time is, that it is going to increase the collisions also. Okay, so average time of collisions or then decreases with increasing in temperature. Okay, so I'll just write the a simple kind of a thing. Okay, so if we increase the temperature, okay, so the speed of the electrons also increase. Okay, that means your number of collisions is going to increase. Okay, so collision increase. Okay, so if the collisions increase, then your tau is going to decrease. Okay, that is the time of between the collisions. Okay, that is going to decrease, and then if your tau is decreasing, that means your resistivity will increase. Okay, because it has an inverse relationship with the resistivity. Okay, and in a metal, N is not dependent on temperature. Okay, so the decrease in the value of tau with rise in temperature causes resistivity to increase. Okay, so in a metal, if you start increasing the temperature of a metal, your relaxation time is going to decrease and your resistivity of that metal is going to increase. Okay, but when in the because the metal, okay, in a metal the number of electrons is not going to influence the resistivity, but it's the case for insulators and semiconductors is different. Okay, so where your number of electrons is going to increase with temperature, and with this increase, okay, this increase will compensate the decrease in the the tau that is there. Okay, and then you can see that again, because the number of n is increasing, your resistivity is going to decrease. Okay, so this part is for the metals. Okay, now if we are considering insulators and the semiconductors, okay, so that means that n will increase. Okay, with temperature rise, your N will increase, and due to the inverse relationship, your resistivity is going to decrease. Okay, so resistivity decreases with respect to temperature for insulators and semiconductors, while the opposite happens, that if the temperature is increased, your resistivity is going to increase. So this is the temperature dependence of resistivity. Okay, and this is again obviously as you can see that due to it's the it varies from material to material, and that is why again this is an important factor for us to know, so that we can design the desirable the circuits as per our use. Now we come to electrical energy and power. Okay, so even before, when we were learning about static charges and electrostatic force and the electrostatic field, we saw that there is some energy, okay, that was being stored, because we were trying to move one charge from we were trying to bring a charge from one point to another point, and the work was being done against the work was being done against the field that was there. Okay, and the work that was being done, it was getting saved in the charge as the charge's potential energy. Okay, so there was energy being stored there, and then it would get converted okay, because there is energy conservation, in play. So similarly, when we are considering this current electricity, okay, so there is obviously going to be potential energy, being stored, or or being converted. Okay, so to understand that, we will consider, say, a conductor, okay, with two endpoints A, okay, and this is A and B. Okay, so and we are seeing that the current I is flowing from A to B. Okay, so this is I, so current is flowing from A to B. Okay, so there is going to be an electric potential at A, and there is going to be an electric potential at B. Okay, so this is going to be VA, okay, and this is going to be a VB. Okay, now since we are seeing that the current is flowing from A to B, okay, so the potential at A is going to be more than the potential at B. Okay, so hence the potential difference between the two endpoints, we can give it as VA minus VB, which is going to be more than 0. Okay, because they are different. Okay, there is a potential difference that exists between them. Okay, and it is going to be more than 0. Now suppose we try to, we take a small time interval, say del t. Okay, so at del t, the amount of charge that is traveling from A to B, if you remember that we had studied in the first class, that I, is equals to q by t. Okay, so now if you're considering the time interval del t, so your del q, okay, so the amount of charge that is passing through the conductor because of the flow of the current, okay, through the time interval del t is going to be given as del q is equals to I into del t, okay, which is traveling from A and B. So the potential energy of the charge at A, okay, by definition will be QV. Okay, we had already seen this in the last class. Okay, that U is going to be the U is going to be the product of the charge and the potential at the at the point. And so you will have UA, or the potential energy at A, as QVA, and the potential energy at B you are going to denote it as QVB. Okay, and the change in its potential. Okay, so there is going to be change in the potential energy because of the transfer of charges from A to B, that you can give as the final potential energy minus initial potential energy. Okay, so the final point is the B, since it's traveling from A to B, so that we put VB, okay, minus VA, and we take the del Q out. Okay, and we know that this is we saw that VA minus VB is equals to V. Okay, so now since we have changed the position of VB and VA, we put the minus sign. So the change in the potential energy due to the transfer of charges from A to B, as the current is flowing from A to B, is going to be minus del Q by V. Okay, and we can see that the potential. Okay, then if we put the the formula for del Q as we had seen before. Okay, so I minus IV del T, and that is going to be less than 0. Okay, that's a negative sign, so the U potential is going to be less than 0. Okay, now if the charges are being moved without collisions, okay, so their kinetic energy would also change. Okay, so because there are no collisions, the kinetic energy would be changed. Okay, because of the because the total energy remains has to be remaining unchanged. Okay, because we have the conservation of energy that we have to take care of. So then we can see that the change in the kinetic energy is going to be the negative of the change in the potential energy. So over here we can then putting the same values over here for U potential in the del K formula, del K is equals to IV del T, that is going to be more than 0. Okay, so actually the potential energy difference and the kinetic energy difference has to balance out. Okay, so that is why we can write in this form. So in this case, okay, the charges where they were moving freely through the conductor, and there was the electric field which was influencing them, the kinetic energy would increase as they move. Okay, so and we have before we had seen that charge carriers do not move with acceleration but with a steady drift velocity. We had learnt about the drift velocity, okay, of the charges under the action of the electric field, okay, where the current is flowing. So since we are saying that there is a steady current, okay, and the kinetic energy would increase as they are moving, but there is no acceleration. Okay, so this happens because of collisions between the ions and the atoms during the transit. So while these collisions are happening, the charges are gaining some energy and it is shared with the atoms. So because of which the atoms, because now they have the energy, so they are going to vibrate, and because of that, obviously there is going to be a rise in the temperature, and then again we know that the rise of the temperature is going to have an effect. But we see that the heat that is being generated because of the vibration of the atoms, it will be dissipated, okay, during the time where the current is flowing. Okay, so then so if you want to calculate how much of the energy is getting dissipated as heat, okay, in the conductor during the time interval del T, we can give it as the the work being done. Okay, so the del W is equals to IV del T. So this is your potential energy. Uh, okay, your energy, not potential energy, your energy that is getting dissipated. So how do we define power? Power is the energy dissipated per unit time. So your P is equals to del W by del T. Okay, now if you put the del W value in this formula, you are going to be left with IV. Okay, so that is current into your voltage drop across. Okay, now we know that V is equals to IR as per the Ohm's law. So finally we can put that the power, okay, so the power loss in the conductor, okay, due to the passage of the current, okay, and the charge transfer from A to B can be given as I square R or V square by R. Okay, so you can see that the power is directly related to the square of the current, and it is inversely related to it is also directly related, it is inversely related to the resistance. Okay, so actually it depends on your the current that is flowing and as well as the voltage that is there. So the power loss that we see is also called the ohmic loss, okay, in the conductor of a resistance R that is carrying the current I. Okay, so the power which is getting heated up over here, like for example, if you consider the coil of the electric bulb, okay, so it is radiating both heat and light. Okay, so there is a conversion of the form of energy, also the form of the power. Okay, so this expression actually shows you the dependence of the power dissipated in the resistor R on the current through it and the voltage across it. Okay, so as I said that P is influenced, or P is related to the square of the current as well as the square of the voltage. Okay, and as per that it can vary either directly with the resistance or inversely with the resistance. So you can see that this equation, okay, this equation P is equals to I square R is equals to V square R, it has an important application to the power transmission. Okay, so electric power that is being transmitted from, say, power stations to our, domestic purpose uses or homes, factories, okay, which can be, obviously, the transformers are situated very far away from where one uses the, the power that we need. Okay, so that is done via transmission cables, and you can say that we want to minimize the power loss. Okay, you can see like as it is dependent on the resistance. Okay, and the resistance in itself is dependent on the dimensions of the body through which the current is passing. So we have to reduce the power loss, okay, in the transmission cables connecting the power stations to the homes. So how do we do that? So we are going to consider a device. Okay, so you can consider the device being called R. Okay, R, and a power P is to be delivered. Okay, so we are suppose using an appliance R, okay, or a device R, and we need a P power to be delivered to R, okay, for R to work through transmission cables. Okay, so the transmission cables have a resistance of RC. Okay, so the power that is flowing, sorry, the power that is generated because of the current that is passing through the transmission cables of RC. Okay, so it will be dissipated, as we saw, the power will be dissipated. Okay, but how much do you what kind of um, how do we minimize the power loss so that the required amount reaches the device R? So then again we see that P, okay, the power is is equal to VI. It depends on the voltage and the current that is passing. Okay, so the connecting wires from the power station to the device, obviously, as we said, that it has a RC resistance. Okay, so the power dissipated, we can again use the formula that we had seen in the last slide, that is I square RC, or you have or okay, in terms of say the power. Okay, so this is PC. Okay, so this is the power loss that we are seeing in the cable. Okay, so I square RC is equals to P square RC by V square. Okay, so actually we are putting the values that we saw in the previously derived equation. Okay, so we can say that to drive a device of power P, okay, to drive a piece of a device of power P, the power wasted in the connecting wires is inversely proportional to V square. Okay, so that means that PC, okay, so the power that is being lost by the transmission cables or the connecting wires, okay, so that is actually the inversely proportional to the square of the voltage. So since now these power stations could be very, very far away from the the place where we want it, and even the resistance is kind of a considerable value. So to reduce PC, we have to ensure that the amount of voltage that is being passed through the wires actually are huge in value. Okay, so that is why we say that high voltage danger signs are there on transmission lines. If you have seen the the power lines that we see, okay, above buildings on the roads, they are going from, they are called high transmission lines because they're actually carrying a very high voltage of current passing through those wires that is required so that we can compensate for the power loss, okay, when we are trying to transfer a certain amount of power that is required by the device. Okay, so some power is going to get lost due to the transmission, and to compensate for that so that it does not affect the amount of power that we are receiving. Okay, so for that we need a high voltage. current that is being passed. So using electricity at such voltages is not safe. Okay, and we have the power is being transported or transmitted through cables to a transformer. Okay, so since now this is very high voltage, okay, so the voltage is very high. Okay, but this high voltage current is not actually supposed to be used by our small appliances or whatever appliances we are using. Okay, so this requires low voltage current. Okay, does not require a high voltage current. So this device in between, okay, where it can be transformed, okay, where the high voltage is reduced to a suitable voltage that is required for home purposes. Okay, so these are called transformers. Okay, so this is what we understand with respect to electrical energy and power. Okay, that is associated with the current that is flowing through a material or a cable or a conductor, and the power loss that happens because of the energy being conserved and converted. Okay, and obviously that again depends on the material, it depends on the distance between where the power, where the where you're generating, from where the transfer is happening. Now we had learned, like whatever we have learned till now, we consider usually resistances, okay, individual resistances. If you remember, when we were doing the capacitance, we learned about capacitors. Okay, so capacitors are a certain sort of a device and resistors are a certain sort of device, but all of these, or both of these, they can be arranged in some combination or the other, okay, which either will increase the voltage that is being passed through the circuit, or it can the voltage that we see across the circuit, either it can be increased or it can be decreased as per our requirement. Okay, so how do we know that which combination is required, to either to increase the voltage or decrease the voltage? So we are going to again learn two kinds of combinations, that is in series and parallel. Okay, so we know that the current, okay, is that is flowing through a resistors is going to be proportional to the voltage. Okay, so that is going to be V is equals to IR. Okay, so this is our Ohm's law, or we can, if you want to know in terms of I, that is going to be I is equals to V by R. Okay, so sometimes the resistors are joined together. Okay, and if the resistors are joined together, suppose I draw this. Okay, so you have your R1, okay, and this you have R2, okay, and I that is flow. Okay, so the same current is flowing through both the resistors, okay, but the potential difference across each of these resistors is going to be different. Okay, so how can we then denote it? Suppose these two are put in series, okay, in a continuous pattern, okay, next to each other. So the charge that is leaving this R1, okay, now the charge that is exiting from here is the charge that is entering the R2. Okay, so the current, okay, it is the rate of the flow of charge, okay, and the same current is flowing from, say, through R1 and R2. Okay, so we can say that the voltage is then differing. Okay, so the amount of charge has to remain same. Okay, since the same I is going through both. Okay, so if the charge is remaining the same and the current needs to remain the same, then the voltage that is there across each resistor is going to differ. So then you have V1 and V2. Okay, so the same current is flowing, so V1 is equals to IR1. Okay, and R2 is going to be V2 is equals to IR2. Now if we combine, okay, we want to see the total voltage volt difference or potential difference between the two resistors. We are going to write it as V is equals to V1 plus. So you can see that V is equals to I R1 plus R2. So if you take I over here, V by I, it gives you the equivalent resistance, okay, of the equivalent resistance, which becomes the sum of the individual resistances of the resistors. Okay, so that very simply you can see over here, R equivalent is equals to V by R is equals to R1 plus R2. And if you keep increasing the number of resistors, you can see that the equivalent uh, or the voltage, okay, so the equivalent voltage that is, you know, passing or that is seen, okay, from one end of the circuit to the other end of the circuit, okay, so that is going to be related to the sum of the individual resistors that is there in the circuit. Okay, so this you can, the sum, okay, of these individual resistors, you can denote it as R equivalent. Okay, so that is for the series. So for a series, R equivalent is equals to R1 plus R2, and you know, all the way up to n number of resistors when you have n number of resistors. Similarly, we can see okay, in the previous you can see that, you know, if your you know, it's kind of directly dependent on the you know, the resistance, the equivalent resistance. Okay, so if your this n number of resistors keep increasing, obviously your resistances is also, the equivalent resistance is also going to increase. Okay, and you can see that the voltage drop across is going to you know, vary with respect to that. Now if suppose you have two resistors, okay, so they are set to be sorry, this is actually, this is supposed to, this is for the previous slide. Okay, so the first this is not for this, okay, the first hole. Okay, this is for the previous slide. I'll put this in the previous slide. Okay, so now we are going to consider the parallel combination. So in parallel combination, what happens is, okay, so you have, okay, so suppose you have a resistor here R1. Okay, so I'm not drawing it right now because it's a bit difficult. Okay, so suppose you have R1 and R2 here. Okay, and you have the current flowing. Okay, so these are actually connected, you know, below one another. Okay, so these are in parallel combination. Okay, so your I is flowing through here this way. Okay, and over here again, the same I is going to flow. Okay, but since now we have the resistors, okay, they have been joined, or they have been connected in the, you know, kind of parallel fashion. The current over here gets bifurcated into two. Okay, so the current through R1 is going to be I1, and the current through R2 is going to be I2. Okay, but the voltage, okay, across both of these, you know, this combination is going to remain the same. Okay, so V remains the same over here. Okay, so now we try to find out the, you know, in terms of the, we first find out the equivalent I. Okay, so because we can see that there are two different, you know, current that can pass through the two different resistors which are connected in parallel form. Okay, so the I is going through R1 as I1 and I is going through R2 as I2. So the equivalent I can be given as I1 plus I2. Okay, so now V is equals to I1 R1. Okay, so I1 is going to be V by R1. Okay, and similarly you can say that I2 is going to be V by R2. Okay, so we put the values of I1, I2 in this equation, and what we get is V by R1 plus V by R2. Okay, if you take the V common, you are left with 1 by R1 plus 1 by R2. Okay, so the equivalent resistance of the entire combination, okay, this parallel resistor combination is going to be, if we call it as Req. Okay, then by Ohm's law, okay, so the equivalent current is equals to the voltage drop across the combination divided by equivalent resistance. Okay, over here we can see, you know, if we keep if we consider this kind of the equation, okay, so I is equals to 1 by R1 plus 1 by R2. Okay, so if you take this over here, so what you're left with is I by V. Okay, so I by V is going to be equal to as the equivalent of the parallel combination. So Req is equals to 1 by V, that is equals to this 1 by R1 plus 1 by R2. Okay, so this is how you can find the equivalent resistance. Okay, when you have the resistors which are connected in the parallel form. Okay, so similarly as we had in the series, okay, so that is going to be R1 plus R2 plus dot 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 till Rn. Okay, so that's a sum of the resistors. Over here the equivalent resistance in the parallel combination can be given as the sums of the reciprocals of, okay, so the reciprocal of the equivalent resistance in the parallel combination is equal to the sum of the reciprocal of each of the resistance of the resistors. Okay, so that is how we can find the equivalent resistance when n number of resistors are put in the parallel. So now we come to cells. Okay, cell, battery, what is a cell? Okay, so usually there needs to be some device or some way through which we can pass the steady current, okay, in an electric circuit. In electrostatic we were only considering static electric charges that are just there, okay, but for current electricity, as we said before, we are trying to consider a steady current that is flowing. Okay, so the device that is used to maintain a steady current in an electric circuit is actually an electrolytic cell. Okay, so in electrolytic cell, you usually have two electrodes, positive and negative, and it is filled with a solution that is called an electrolytic solution, and this solution has negative ions and positive ions in it. Okay, and the electrodes also, one is going to be positive, okay, P and N. Okay, so the positive is P and the negative is N. Okay, and suppose we have dipped the two electrodes in the electrolytic solution. Okay, and because if we pass a current through it, okay, so your positive electrode will get positively charged, your negative electrode will get negatively charged, and the negative and positive ions in the electrolyte start moving, and they actually contribute to the current that then flows through the circuit. Okay, so you can see that the positive electrode has a potential difference P, V positive, that will be more than 0 because it's positive, and similarly your negative potential that is going to be a negative V negative. Okay, so since we are considering the negative sign, okay, so the V negative could be 0 or more than 0. Okay, and in total the N electrode will have negative potential. Okay, so this is relative to the electrolytes. Okay, that is it. So when there is no current, okay, so the electrolyte will have the same potential throughout. So the potential difference that will be between P and N is actually going to be only the difference in the potential of the two electrodes. Okay, so the electrolytic potential will have no effect since there is no current. The electrolyte is going to have the same potential in the entire solution. Okay. So this potential difference that we see between the two electrodes, okay, when they are put in the electrolytic solution and there is no current passing, that is called the EMF or electromotive force of the cell. Okay, so we are denoting it in the terms of epsilon or E. Okay, so that is V positive plus V minus, and usually that is more than 0. Okay. So actually you can see that this is the the electrolytic cell that we were talking about. And in a circuit, you kind of refer to this cell in the, this symbol of, a cell where the longer line is the positive electrode and the smaller line is the negative electrode. Okay. So this is and the connections is made with respect to the a resistor. Okay. So this is how you symbolically present a cell. Okay. And this cell will have an EMF. Okay, so which is the potential difference between the two electrodes when there is no current passing through it. Okay, so the electrolytic solution does not, there is no potential change. It has the same potential. Okay, so to understand the significance of the, this electromotive force. Okay, first of all, this electromotive force, we are calling it force, but it is the potential difference, as you saw in the, in the formula. It is not a force, it is a potential difference. Okay, so we are just, it was called electromotive force. Okay, so whoever kind of, found this out gave it the electromotive force. Okay, so suppose again, you consider a resistor R that is connected across a cell and a current I is flowing through, across R from C to D. Okay, so suppose this is, sorry, it is already marked in the diagram. So this is point C, this is point D. Okay, and the current is flowing through C and D. And the steady current is maintained because the current is flowing from N to P through the electrolyte. Okay, so in the electrolyte it's going from N to P, and because of that the current is then flowing from P to C and from C to D through the R and then D to N. Okay, so this the entire this is getting, kind of connected. Okay, so the steady current is maintained because the current is flowing from N to P through the electrolyte, and the current I flows across R from C to D. Okay, so across the electrolyte the same current is flowing but in the opposite direction. Okay, and whereas through R it flows from positive to negative electrode. Okay, so if we consider, when there is a finite resistance R, okay, of the electrolyte, we did not consider the resistance that is existing in the electrolyte. Okay, so we are calling it R. That is the internal resistance of the cell. Okay, so in the first situation, your big R is say infinite. Okay, so this resistor. So I is equals to V by R is equals to 0. Okay, so where V is a potential difference between P and N. Okay, and now, so what is going to be V? Okay, so that is going to be potential difference between P to A, between P and A. Okay, this is a point in electrolytic solution. Okay, and this B is also a point in the electrolytic solution next to the negative electrode. Okay, so the potential difference between P and A plus potential difference between A and B. Okay, and the potential difference between B and N. Okay, all of these, addition of this is going to give you the total potential difference between the two electrodes, which, as we mentioned before, is the electromotive force or the EMF of the cell. That is why we are saying that EMF is the potential difference between the positive and negative electrodes, okay, in an open circuit. That is when the current is not flowing. We are this situation that we are considering when the current is not flowing. Okay, and if R is finite, then I is not 0. Okay, if there is a resistance that is there, so okay, so the current that is passing is not 0. Okay, and in that case, the difference, the potential difference, the E or the V between P and N, it can be given as the difference in the potential of the electrodes. Okay, and minus it with from the voltage of the with respect to the internal resistance of the cell. So then what you're left with, okay, so the potential difference between P and N is going to be the EMF, okay, minus current into the internal resistance of the electrode. Okay, so the negative expression for IR, okay, is, is of consideration. Why? Because now the current is flowing from B to A in the electrolyte. Okay, that is why there is the negative sign, okay, which is, opposing the current flow between the, through the resistor. Okay, so the current I is flowing B to A in the electrolyte. The internal resistance of the cell sometimes is, it is kind of neglected because the EMF itself is much, much higher than the internal resistance of the cell. Okay, so we will stop here today, and in the next class, that is tomorrow, we are going to learn more about the internal resistance of the cell, and then we will move on to the if now what will happen if we arrange such cells in series and parallel combination, and then we are going to see some designs of circuits and also Kirchhoff's rules, Kirchhoff's law. Okay. So thank you.